2, 1. So welcome to the introduction to vector fields. So I am going to make some assumptions. I'm assuming that you are a physics student and you're taking physics, kind of the foundation of physics. And this video is intended actually for kind of grade 11 and grade 12 students who have never really seen this concept of vector fields. I'm going to assume that you have studied the law of gravity, okay? So Newton's law of gravitational pull between two masses. So as you can see there on the actual screen, so I have provided the formula there. Now, if you have not, I'll put up a link up above there. So you definitely should kind of refresh that concept so that you understand it, because I will make the assumption, okay, that you are familiar with this, because it's a nice starting point in order to try to see what these vector fields, and in particular, the vector field lines, are all about. So let's kind of get started. So the first thing that I would want to remind you of is that when you are calculating what the actual force will be with regards to two bodies, okay, so mass number 1 and mass number 2, these two particular bodies, okay, so that you have, are going to be separated by a certain distance. Now, for the sake of this video, so to make it much nicer and cleaner, so I'm going to assume that one of these masses, at least initially, okay, is going to be the mass of the Earth. Okay, so I'm going to refer to that as ME. Now, because we're kind of stuck on the planet, okay, unless you are, somewhere in space, well, then you know that we are going to always feel this pull which the Earth kind of has on us. But the truth is that, okay, the actual force is present between both bodies. So, for example, ourselves, okay, and the Earth as well. Now, what is this concept of these vector fields? And in particular, so notice I'm kind of going to be referring to the gravitational vector field, okay, which is related to the forces that we have. So if you take the Earth itself, and let's imagine, here's our Earth right there, you know that if you're going to be standing on the Earth, now it doesn't really matter where you are. So, let's say that you are somewhere, okay, right here, or if you're somewhere right here, okay, or somewhere right here, or right here, it doesn't really matter. We can go all the way around. We know that there's going to be a pull that you have. Now, with respect to this particular equation for the force itself, so here the radius, okay, that we have, or sometimes it's referred to as the distance. So I'm going to kind of break it down into two components. So everyone should be okay in thinking about, okay, one of these masses is the mass of the Earth, all right? So check, okay, so that mass of the Earth I'm going to be designated as ME. Okay, the other mass, you can imagine it's you, okay, or a 1 kilogram mass, it does not matter, okay? So one of the other masses is going to be the mass of an object. So I'm going to put mass of an object, I'll put a little O, okay, for the object itself. So that's going to be your mass M1 and mass M2. This radius that I have in there, so that particular radius R, I'm going to break it down into two things. I'm going to break it down to the radius of the Earth, because it is with respect to, so here, what I'm referring to is, so here's the center right there, and this would have been the radius of the Earth itself, okay, so that's what you would have right there, so I'm going to refer to that. Now, if you are standing at any of these points right here, you know that you can calculate exactly what the force will be between, the mass of the object, okay, and the Earth itself. Now, you might say, well, I'm standing on the Earth, so, the radius in between us, there is no radius in between us. No, there is, okay? So this particular radius in the equation is referring to the centers. So it's the center of the Earth, right? So this is from right here. So this is the distance from here to wherever it is that you're standing. So that's the radius. Now, in this case, this radius would have been just simply RE, all right? So now that we have kind of those notations out of the way, well, what I'm going to introduce is that the entire radius is going to be the radius of the Earth plus okay, whatever distance away that you are. So for instance, okay, so if you're going to be kind of standing a little bit further out, okay, so you can kind of, maybe you're somewhere up into space over here, well, then this is going to be the radius of the Earth plus the actual distance. So this is the distance, and this is the radius of the Earth. So that's what you have right there. All right. Now, it doesn't matter where you are. You know, you can be right here, you can be on the Earth, you can be further away, you can be really out into space, okay? It doesn't matter. You can be all the way around, okay? So somewhere right there. So that's what we are going to try to think about, okay, in terms of, so this is RD right there, so that's the distance, and the combination, okay, so the addition between the two is going to be the distance between you, the object, and the Earth, or the center of the Earth that we have. All right, okay, great. Now, so once we have that, we have this wonderful equation, okay, so basically through experimentation, notice that this G, okay, is the constant of kind of gravitational pull between any two objects, and we have it right there. So it's very tiny, okay, right here, and we have all of these particular units in here. So at any distance that we like to have, we can calculate what will be the force. Now, you know that the force between you and the Earth is going to be a pulling force. So, for instance, if, for instance, you were somewhere out into space over here, okay, you know that there would have been an actual force which is going to try to draw you in, okay, in towards the center of the Earth. Well, so this is the force of the gravity that we have, and it is indeed towards the center of the Earth. So, for instance, you know, this would have been exactly towards the center. Now, if you are going to be somewhere out, okay, on the other side, so let's say over here, well, once again, you know, you can actually calculate what that force will be between you and the Earth. And again, it would have been towards the center. So what you're noticing is, and I hope that you're noticing, no matter where you are, the actual direction is always towards the center. So that's what actually happens, regardless of where you might actually be. And we can calculate exactly what that force will be, right? So that particular force is just governed by this equation. And mass 1 we can obtain, mass 2 is the mass of the Earth, okay? R is going to be the radius, or the distance between you and the center of the Earth, and we have what the force is. So now, no matter where you are, or how close or how far away you would be, this entire picture is going to look something like this. So I'm going to bring out decimals, and so here, let's imagine this is my Earth right there. I'm going to kind of shrink it a little bit. And I have kind of coded in on the left-hand side, okay, so within here, so you'll notice, okay, on the left at the top, okay, you have the actual force that is present. Now I'm going to talk about this momentarily, but I just want to be able to show you, okay, so what happens. So here is, you know, so here's a bunch of points, okay, and those particular points, so this is where you might be standing on the Earth, right? And now, what I want to be able to depict for you is this concept of this vector field. So if you're going to be standing right there, you know that the actual force is going to be towards the center. And now, if you, let's say we're kind of now spreading apart and getting further away from the Earth, so this is kind of the way that it would look like, you notice that you would have this pull. So notice it's creating these vectors, okay? So it's basically this directional vectors, and all of them are towards the center. Doesn't matter how far you are from the Earth. So notice it's going to create, you know, this nice, beautiful image, okay, that I have kind of coded in here, where, you know, these things are kind of spreading out, and they're creating this vector field. So now these are imaginary, of course, you know, we are just drawing them in, but for every point that you have, okay, you know that the direction would be towards the center. And this image that you are now seeing, okay, is a creation of vector field lines. So So this creates a field, because you can think of a field like a wheat field, for example, right, on a farm where you have all kinds, okay, of crop all the way. So it's a field. Well, in this case, we have a field all the way around the Earth between any object that you would place, and we're drawing out these lines which actually show us what would happen to that object if we let it go. So if we would let it go and it was just the Earth and the object, then basically these two things would just kind of come together and would be pointing it towards. And it doesn't matter how far you are, you're still going to have these vector fields, okay, that are pointing out. So now with these vector fields, let me go back into here and try to explain those to you. So as you're kind of passing through, so what we would do is we would do something like this if indeed it was, for example, the Earth and the gravitational pull. So you would have your Earth right there, and in order to draw your vector fields, all you would have to do is you would have to kind of show them so that they would be pointing towards the center. And you're now drawing out, so this is called a vector field lines, okay, that you have, and all of them, so you would continue this all the way through to show what that vector field is. And this would continue all the way around. Now, of course, you can keep them more dense, you can keep them less sparse, so that depends. Sometimes if we keep it more dense, it means that in those instances, the actual vector fields or maybe the forces are much stronger, right? So you have, sometimes we'll see it like this. Sometimes you might see these actual vector fields, instead of drawing out the vector field lines all the way through, you might actually draw them out kind of as arrows, okay, as you're going through. And these arrows are now showing you what the strength is, okay, as you're going through there. So instead of drawing them as one field line, so the line is all the way from the starting point to the end, what you're doing is you're now drawing these as just smaller vector fields. And as this would continue on, these vector fields would get a little bit smaller and smaller and smaller, okay, all the way through. Why would they get smaller in distance? Because the magnitude is decreasing with regards to this particular force that we would have. Notice that because the radius, okay, or the distance between the two is now squared, that is in the denominator, then what it will cause is the further you are from the Earth, the smaller the magnitude becomes, okay? Now, so far I have shown you between an object, okay, and the Earth. Of course, this works for any two objects. And in particular, when we talk about the vector field lines or the gravitational vector field, in general, you typically will draw it and you will talk about it not with regards to any two specific items, but instead what you would do is the following. You would say that you have, all right, so I know what my force would be, so that would have been just G multiplied by the mass of the object multiplied by the mass of the Earth, in our case, divided by, and now I've changed this up, so this is going to be my entire, this is the radius of the Earth, plus, the distance that you are away from the Earth squared, right? So I've just substituted this back into here. So if we have this, and we start putting this in here, then what we like to do in physics, instead of it having very specifically for the two objects, what we want to be able to do and say is, well, what would be the actual force, okay, per each of the masses that we have. So what I will do now is I'm going to divide this by the mass of the object. So if you have a mass of the object in the numerator and in the denominator, then what will happen is these two will cancel. And what you're going to now come out with in general, this is going to be just G multiplied by the mass of the Earth divided by, so all of this right here that we would have, I'm going to duplicate it, put it underneath, and you might say, well, so that's different. Well, indeed, it is different, because what we're now doing is, if you recall, this entire thing would give us what the force would be in newtons, if you're talking about metric standard units. And if you divide by a mass right there, well, this particular mass is in kilograms. So what that would give us now all of a sudden, so this now is no longer in newtons. So I'm going to duplicate it, bring it back down here. And now what this is called is the force gravitational field, okay, that we have. Now I called it GE, okay, so within here. So this is with respect to the Earth, right? So this is the gravitational field with respect to the Earth itself. And the unit here, notice, is going to be newtons per kilogram because I divided by the mass of the object. Now, what this allows us to do, now because this is the force per each kilogram that you have. So no matter where now you put the object, if it's here, if it's here, you know, if it's here, if it's here, and you want to know what would be the force that the object would experience at this particular point, well, this right here now gives you what the actual vector field is per each kilogram. So we know that at this point it would be pointing in this direction and it would have this magnitude per each kilogram. So now if we know it per each kilogram, we can then multiply it by any mass we like, and then we will know exactly what the force will be overall. So I just want to show you, because this is exactly what I did in decimals. So in decimals, as you are looking at these field lines that are pointing, these vector field lines that are going through, if you look on the left-hand side, so notice that what I have done is I have calculated the actual vector field with respect to the Earth. So if you see on the left, okay, so I'll just kind of zoom up there, okay, all the way, bring it to the top, and notice it's calculating the value for me. And what I've done is I have said, okay, well, what is the force per each kilogram? And that is now creating a vector field that you would have. Per each kilogram, that would have been the force. But if you recall from Newton's second law, right? So newtons per kilogram, the unit for that is actually meters per second squared, which is the acceleration, which is really cool to be able to see. And that's why on the top left, you can see there that it says 9.81, 335, etc. So this is the amount of force per each kilogram that you would feel. And of course, it's going to be equivalent to the, gravity, G, because we're doing it per kilogram. And notice that it will change now, as I'm going through here. So this all the way close, this is basically saying, so that D, I've just moved it. So I'm about 16.6 meters away from the Earth. Well, of course, if I'm going to be, to 30 meters and so on, it's going to change. But notice, on the left, as it's changing the FGE, it's not changing much because we're not very far away from the Earth. But if you would change that, right, and you would actually compute it, and instead of saying, you're 70 meters away, now notice if I'm going to say, now we're 700 meters away, so we have these beautiful field lines. Notice now they're expanding all the way through there, as you're going through. So that's 700 meters away. Now, what about if we are 7,000, so 7 kilometers away from the Earth? Notice what happens. That basically the further you are, now all of a sudden, that vector field is no longer 9.8. Notice it's 9.79. It's losing its strength because you are further and further away from the Earth. And the gravitational pull is less, of course. And this is captured, by this as you're going through. So within here, if I put, let's say we're 70,000, which would be 70 kilometers away from the Earth, which is still not a huge amount, but notice now it's 9.6. Okay, now all of a sudden, okay, if I'm putting it in there and it's further, now notice it's dropped. So it's no longer 9, now it's under 8. Okay, and as you keep going, notice now all of a sudden it's only 2. So the further and further away you're from the Earth, okay, the pull isn't there. Okay, so it's basically decreasing. And these field lines would be showing that all the way through. So as you're going through there and you want it to be able to capture, that's why as we get further and further, so these vectors might be a little bit bigger, they're showing the magnitude. But as you get further and further distance, these vectors would become smaller. So we would actually show it that they're much smaller arrows, and it would just tell the person who's looking at these that as the further you are away, the magnitude decreases. But we have the direction. In this case, it is all towards the center of the Earth. And it's a really nice and magical thing that we have in here, that we can create this, and it can be per kilogram. And if you want it, okay, per 100 kilograms, you can just multiply and you'll find out exactly what the force will be at any point that you like. So this is the introduction to the gravitational vector force field. You have seen now the actual field lines. These, of course, are all imaginary, right? We draw them so we can actually understand it and see what's happening with the forces and what would happen at any point around the Earth. But, okay, in reality, the force is present, right? But those lines are not, right? So we actually just draw them in. Okay, so that is the introduction that I have for you with respect to these vector fields. And I've just concentrated on the gravitational force field because it is one that you've studied. Typically, when you do dynamics, okay, and you talk about forces, you cover the law of gravity, which is this one. And so I hope that this now makes much more sense to you and you can understand and see these field lines in action. So there you go. So here's the field lines, okay, that we have. You can make them more dense if you like, okay, you can sparse them up, but they're just showing you what is happening around an object. You will also see this as you move over and in particular start studying charges. Now, when you start studying charges, you also will have forces, and you're going to relate it back to Coulomb's law instead of the law of gravity, as you see right here. Thanks for watching. We'll see you in a future video. Bye, everybody.